Hello, everyone, and thanks for coming to the fourth STEM Colloquium here at Cabrillo College. And we have a guest speaker, Vahik. He says we could call him Mike, and he's coming to talk about engineering, and he has done biomimicry. And Mike, go ahead and introduce yourself, and you have the floor for a bit, and we'd like to take some questions at the end, and feel free to put questions in the chat and I can voice them for you if you'd like.
Absolutely. I'm Vaik. I'm an aeronautical engineer. I've been working in a field, in various fields, including teaching, research, and I want to share that with the young generation and with you guys. It's an honor to be here. I want to share you with a perspective of an engineer that looks into nature to learn and do not reuse it. It may be annoying for some project leaders and CEO, but I think we have to be wise and ask Mother Nature, because it is talking, but we don't often listen. We do things, we design things as we have done for many hundreds of years without any change. One good example is the jet engine that has been the same for 60 years. Since Frank Whittle in England designed it, no major changes. So I think we have to learn. We have to adapt and be like nature without leaving a footprint behind us and without polluting as we do now. So that's what I want to share with you guys. Real life applications from engineering with some differential equations, but it should be real life applications of how can you use that knowledge that we have everywhere around us. How can the new generation be inspired? What should they choose? How should they choose their field of study, their major? So those are the things I want to share with you guys, and it's an honor to be here and see so many of you.
Excellent. So let's start with, how did you get into engineering and how did you choose your major? Can you talk about that a little bit before you jump in any further? That really helps focus the students sometimes.
Absolutely. Actually, strangely enough, my passion for engineering and especially aircraft and aeronautics started when I was 5-6 years old. My mom bought a few toys, included aircraft, included Legos. And I happened to also be in a captain seat on our way to my ancestry land, which is Armenia. The pilot asked me to come in because I wanted to see how this big bird flies. That's exactly what I asked him. And he showed me and I was amazed. And I couldn't understand it at that time. I was just 6. But I think when I go back in my memories, that's where my inspiration started. And during my years of studies, I started to become more and more interested. So that's why I chose to study to understand how aircraft flies initially. However, as you all know, aerospace engineers and aeronautical engineers like me don't just design airplanes. Could be anything from heart valves to, I don't know, cars to medical instruments to even hospital equipment and surfaces to, so it is vast compared to 30-40 years ago. And you don't only have to work at Lockheed and Boeing, you can work anywhere almost, since nowadays engineers use mainly simulations, and that can be applied to anything. From insects to aircraft to space shuttles. So that's the power of the knowledge I feel we should have and use.
Awesome. And so it sounds like you've got some stuff prepared for us tonight, and I wanted to let you know that you can share the screen. It should be open for you if you have anything to share, and you have the floor.
Absolutely. I have quite a lot to share. Let's see if we can share the screen, if it works. Okay, here we go. I'm going to try to keep the time. Let me see if I can. Okay, excellent. So here are a few slides. as I said, I'm honored to be invited, and I have many years of experience in engineering, in physics, even in quantum physics. However, every day I learn something new, and every day I'm in awe of Mother Nature that has a lot to teach us if we listen and learn. So if I try to, start with something unusual, with a poem I wrote, especially for this occasion. Not that I have skills in linguistics, but I tried my best. As an engineer, I think it's pretty good. This is to inspire the young generation what education means to me. It's for many of us, education is a privilege. For others, it's a human right. For some, it's a burden of knowledge. For others, it's a gift of eternal power. It's the tree of knowledge and wisdom that always grows as long as you learn. It's the difference between uncertainty, poverty, and darkness, and the future that is bright. It's the future that is bright. It's the key to personal growth. It's the key to transform and change society. It's the key to financial stability. It's the key to achieve mighty things. However, if school is not your calling, look beyond the books, listen to your heart and mind. Life can be the best teacher and educator. As long as you're learning every day, you are growing the eternal tree of knowledge and life. That would be my poem about education to the young generation. So let's start just quickly. As many of us that came from abroad, I arrived here from Sweden, actually, of all places. After flying over Iceland, Greenland, over Canada, Salt Lake City, and so on, and arriving at the City of Angels at LAX. That was, I've been here many, many times. My family moved here from Sweden. I'm originally Armenian, but I grew up in Sweden, which was amazing to me. These are just few pictures from where I grew up. This is a city known as Uppsala in central part of Sweden, not far away from the capital, Stockholm. Beautiful, but beautiful summertime. It's quite cold and windy during the winter, but beautiful. And on the top left corner, it's my favorite city, apart from Barcelona. It's Gothenburg, where I lived, studied, and worked for many years. It's a beautiful coastal and harbor town, similar to San Francisco. And Uppsala, what it's known for, it's university that is one of the oldest. However, the oldest university in the world, as you know, is Bologna in Italy. So this is a quick collage of what I did as a kid growing up in the Arctic country of Sweden, the land of the midnight sun. On the left-hand side, it says Sweden, the land of the midnight sun. So what I did, I had an amazing childhood growing up. Sweden has so many thousands of lakes and forests that you cannot even count. It's unbelievable. I did a lot of fishing, both myself and my family. It was a lot of canoeing, playing in the snow, playing soccer or football, building snow shelters, building tree houses, picking a lot of berries. Sweden has amazing amount of berries in the forest, included white blueberries, cloudberries, and yummy lingonberries, including ice skating on frozen lakes. That is really exotic for many. These are a few things you may recognize from Sweden. Sweden is a tiny country, less population than California, much, much less. But they've done quite a lot of and have had impact around the world for being such a small country. You'll be IKEA, you'll be H&M, you'll be Saab Aerospace that design the fighter jets. You'll be Skanska with the huge construction and civil engineering. It'll be Ericsson with 5G and all the electronics. It'll be Spotify and the music. It'll be Volvo that most of you know for safety and the belt, inventing the belt, and SKF for the ball bearing, and Ericsson that is a giant in tech and electronics. These are just few pictures. I think my mom will like this. It's an interesting picture I found online. It's where I actually grew up. It's a city, small city. However, I came from a very humble background with my family, especially my mom, that have always been there and supported us and give us, especially me, the courage and passion and energy to move forward in life. So these are a few things that I did as a teenager growing up. Definitely bike. Sweden is a very environmentally friendly country. In fact, funny enough, my wife laughs about it. I recently actually got my driving license in US. That's how we use public transport in Sweden. So it's bikes included, using bikes in snow. This is short about Sweden, that has a lot of lakes, about 100,000 lakes. And it has a total of 267,000 islands. That's the most in the world, and a lot of forest. About 57% of Sweden is covered in forest. So it kind of looks like Canada, actually, I would say, very similar to Canada, Sweden. And here are a few pictures you may recognize. The Ice Hotel that is famous around the world, that built this hotel completely from the river ice every year, and it melts and they rebuild it every year. And on the top right corner, you have the beautiful Northern Lights, or Aurora Borealis. And that's thanks to the sun and the ionized particle that hit our atmosphere and get scattered, but they escape through the magnetic shield of the Earth. And around the North and South Pole, you see this beautiful, beautiful dance in the sky, which is, I haven't seen it myself, but I would love to see that because it's really, really, really fascinating. So that was short about Sweden. Influences in my career. Funny enough, it would be actually toys from my childhood. I remember when I close my eyes. It would be definitely aircraft, Lego. It would be train, and the train tracks included the one in wood. So included, as I said, the experience that I had on that flight, sitting in a cockpit with captain was amazing. But I think that's where my career choice started, when I start to think about it. What and who influenced me? Definitely, it's the curiosity to know. I'm still curious. Passion for learning. Definitely parents' encouragement, especially my lovely mom, that always encouraged us to actually learn. And friends. I had few friends as role models. That was important. And I would have to tell all of the young generation that listen to this later that it was the realization that life is a gift. We have one life and chance to get educated, to grow, to live the best life that we can, in harmony and in peace, and to think that we did and achieved the best we could. That's the most important thing, I think. So what should I major in? I get this question. I used to get it when I used to teach and study and do research in England, in London. So what should I major in? I don't know. I'm confused. A lot of students actually brought prints for salary scales for engineers. And I didn't want to make them feel bad, but I used to tell them that actually value and price is two different things. Humans put price on things. So it may be invaluable to you, but for somebody, it has no, so if it's not a price tag, if it's not a salary, people don't associate that in general with having value. But to me, I would say that's my advice to the young generation. Base it on your curiosity and your passion, whatever. For me, it was science. If it's music, if it's dance, if it's linguistic, if it's history, if it's applied art, math, whatever it is, close your eyes and don't look into the statistics of salary scales and so on, or status, because that will not last long. If you go to work Monday morning and are not happy, you have the best salary, but you're not happy. It's not your passion. You won't be good at it. I promise you. If you have the passion and curiosity to know, you will always develop and explore your skills and be the best you can. So that's my advice to you. If you want to know what to major in, close your eyes, listen to your heart and mind. What do you really, really, really enjoy, and what are you passionate about? Whatever that may be. So listen to your voice within you, not in the society, I would say, because that's will scatter your mind and thoughts. So what kind of problems do engineers solve? Actually, this is even confusion amongst the engineers, which is really strange. Engineers and scientists. I often get this question from even some colleagues. What type of engineer are you? When I mention that I'm an aeronautical engineer, and especially in US, they use the aerospace engineering term, they often say, oh, how fascinating, that must be difficult, but what do you actually do? I said, that's an interesting question, but there are many different types of engineers, but few major types, I would say, are civil engineering that solve problem with infrastructure. It's mechanical engineer that solve any problems with engines, motions and systems and robotics. Aerospace or aeronautical engineer like me that solve issues, anything to do with anything that moves in fluids or through space or through Earth's atmosphere. Environmental engineers that look into solving the pollution, the global warming that we have at the moment. Electrical engineers, we have biomedical engineers and chemical engineers, and many, many more, included software engineers. So we have many different types of engineers that are specialized. But I told one of your colleagues that unfortunately, life and reality and industry doesn't work that as used to do for 30 years ago. So if you are a civil engineer, you don't only design bridges for 40 years and that's it, 8 to 5, and that's it, you're a civil engineer. That's not, unfortunately, or I would say fortunately, it's not the way it works in reality in the industry. You have to be able to do multitasking and do multidisciplinary inclusion in any field. So just to give an example, I'm a specialist into anything that flows. Wind loads, current, ocean loads. I worked on wave dynamics. I worked on erosion in seabed and so on. Helicopter, rotor, anything that flows. But when I worked as an engineer to design a floating wind turbine in Sweden a few years ago at a company known as Seatsworld, I realized that I cannot just do what I'm best at. I did that already, but in order to design the best turbine blades in the world, engineers like me should not only understand how the wind behaves, how it rotates, how it generates noise, how it's affected by ice, snow, wind gust, and so on, and even lightning strikes. You need to also broaden your skills and look into materials. So I start to dig into, as a not a background in materials engineering, but I was forced to, because I understood that in order to design the best wind turbine blades, it's not enough to understand how the flow and wind behaves around the rotating wind turbines. You need to understand what type of, how big should this be? What type of materials should you use? Can you minimize it? Can you use less polluting manufacturing methods and so on? So I looked into materials engineering, composite material included carbon and glass fiber and so on. And I learned very quickly that, unfortunately, wind turbines are not that environmentally friendly. The way they generate power is fantastic. It's basically wind that is there thanks to our sun. However, what happens to it during manufacturing of the blades is anything else than environmental friendly. So that's one example to you guys, young generation, that in order to be like Mother Nature, to actually take into account and look at the imprint of any design, we have to look into multidisciplinary fields and subjects. We cannot just do software engineering thing. That's it. I'm a software engineer. I program things, robots that goes into space. What happens to it afterwards, I really do not care. That's not the way I think responsible engineers and scientists should work. We should leave Earth and our design in a better state than it was initially. Few things I want to show you guys amongst the greatest discoveries and accomplishment are this. I would say it's up to anyone, but I've tried to do a collage for you guys. So for those of you who think, what have actually humans achieved? I would say it's a lot. Humans have achieved incredible things, not just thanks to the knowledge. It's actually the drive and perseverance and the curiosity of humans. All humans, not only Leonardo da Vinci and Einstein, but all humans have this ability within them if you listen to your inner voice, but a lot of us don't. A few examples is the DNA from 1953. It's all the Mars landings, incredible feat, especially the latest one from NASA and JPL engineers. It's my absolute favorite still to this day. The landing on the moon in 1969, I have to say, as an engineer, I still get goosebumps. I just cannot still understand to this day how they did it. I know they had a few hundred or a few thousand engineers working on it and a great budget, but do this in 1969. No nation have been able to do that until this day. They are trying, and without capability of a handheld calculator, it's just astonishing. As you know, as I learned through very interesting lecture at MIT about space shuttle design, that all the space shuttle for the Apollo, it was not CAD drawings as we have now. It was hand drawn, thousands of details for the complete space shuttle, included the thermal shields and anything you want. It was hand drawn. That's engineering that they did in 1969. The Russians were well ahead of them, but the Americans did it because they believed they could do it. They had the passion and perseverance, and they did it. They actually landed on the moon in 1969, and that to me is one of the greatest accomplishments of mankind. Next one, 1903, the Wright brothers. Next one, internet from 1983, actually. Next one that is very valid now is the vaccine. 1796 included penicillin and so on. The vaccine have saved millions of lives. Next one is the deep dive from 1960 to the Mariana Trench that is about 11,000 meters deep, which is incredible. The fire, humans started to tame fire about 1.7 to 2 million years ago. That's astonishing. It was not Homo sapiens, it was Homo erectus. 1759, electricity. What would we do without electricity? Well, you tell me. What would we do without printing books, the Gutenberg press from Germany? And language, how will we communicate? Well, sign language, you can use that certainly, but I think that was also a huge part. I know you have few linguistic here that are listening. I think you'll be happy to hear an engineer said, if we didn't have language, I don't know how and if we would actually land on the moon, because how will we be able to communicate our findings, our thoughts with each other in such an efficient way as we do now? So definitely language, about 50 to 150,000 years ago, approximately. It's hard to know when humans started to use language in Africa. And about 4,000 years ago, it was steel, using iron ore and furnaces a few thousand years ago to create and manufacture steel. We have steel everywhere around us, not only in our car, but everywhere. And I have to say, my absolute favorite, you'll be surprised. This one is an absolute surprise. That is not, this is the Atasanov Berry, the digital computer from 1937. It's from Iowa State University, actually. So it was not Apple, it was not Jobs and Bill Gates. It was back in 1937. That's the start of digital computing, and that's how big it was. However, my absolute favorite, and I'm absolutely serious about this, this is more than 2,000 years old computer. If you don't believe me, search for this. It's the Antikythera mechanism from the ocean bed. It was found a few years ago. It's the ancient Greeks that for 2,000 years ago designed an astronomical tool that is extremely complex. And it is a 2,000 years old analog computer. Well, if that doesn't amaze you, I don't know what will. So humans actually designed and created a computer 2,000 years ago. This is before Jesus. That's unbelievable to me. And it was found on an ocean bed. It's they're still actually trying to understand how it worked, but it's extremely fascinating to me. So what's my background? I'm an, as I said, aeronautical engineer. I have a Master of Philosophy in Science, a Bachelor and Associate degree. But I also tried to study physics because I think physics is the basis of everything, including quantum physics. It may be complicated, but to understand the word, I think you need to understand a little bit of physics. I often laugh and joke with my wife. She said it was fascinating. She asked me, what was the most fascinating things that you learned in quantum physics? I said it was to understand why a red rose is red. And she started laughing. I said, what do you mean? Red rose is simply red. I said, yeah, but why is it red? So that was fascinating that our lecturer came in with actually a red rose, a professor, and said, well, forget about this wave equations. I want you guys to explain why is this rose red? Can you explain that? That's the type of thinking and philosophy I want all of the students to have, to be curious and ask why. And the reason is basically that a red rose, it has pigments that absorbs all the spectrum. As you know, light is an electromagnetic wave, like ocean waves, but it's the wave of light. It's an electromagnetic wave. So it basically absorbs all the rest of the spectrum of the colors except the red spectrum, the red wavelength. So that is reflected from the red rose into your eyes, into the optical nerve, into our brain, and voila, we see a red rose. And the same goes with many things, although some things like the peacock feather that are my absolute favorite is not actually a pigment, it's known as structured color. So that's completely different story. It's due to the microscopic structure and the way it reflects light. It's not a pigment. So peacock is actually brown in its base, but the shimmering, beautiful color is not actually a pigment. It's the structure of its feather in the microscopic structure. However, these are few books I studied. I definitely don't, I would lie if I say I remember it. I often get this question from students I supervised, especially in Sweden and England. Do I need to remember all the differential equations and all the books? I said, no, nobody in the world can remember this. However, you should definitely remember the fundamental and basics and be curious, ask questions why. And you can always search for information, especially now online. So it's not to knowing all these books and all the equations. No, actually, that's not the vital things. If you ask me as an engineer in the field for 20 years, is actually to learn and train your mind to look beyond the books and ask questions and try to predict things, trying to be inventive and try to learn from nature. So information is widely available now. This is a funny picture. I used to scare some students. These are some differential equations known as Navier-Stokes equations. Everyone that does fluid dynamics like me knows, so I often get actually this question, do I need to solve these equations as a student or for the exam, or do you use this as an engineer? The short answer is no, you don't actually. The computer nowadays does the job. If we would solve these equations, it would take us 100 of hours compared to a few hours that a supercomputer can do to actually solve this equation for us. These are a few pictures from my studies especially in London, as a first student and as a research engineer in the lab. That's me in the aeronautics lab in London, trying to mount pressure sensors on a section of, this is a section of a wing inside a wind tunnel. So you have a huge hairdryer, basically, as I call it. And these are a few of our technicians and the instrument. I spent many 100 hours. My research friend, Chris Singh from Singapore. And here are my, one of, or two of my funniest students, Dominic from Ghana, that always used to have nice tie, despite that he was students, which I thought it was hilarious and funny. And Yanis, the Greek that was glued to his computer, despite that I told him you need to refresh your mind and memories in order to be able to solve them. So these are my past students. So what was the outcome of all the knowledge and studies? A few research papers, but it was more of the realization, not the actual papers itself, the research I conducted. It was more that it made me think how much actually we don't know. We have a huge and vast knowledge, but how much we really don't understand about nature and things. We can design them, but we don't actually in detail understand them. Next one, my involvement in AeroE. My friend from AeroE is here, Ken. He's the one actually that inspired us and treated us like his family. And when I came to US a few years ago to live here, as I said, I've been visiting here due to my family for many years. And I know all the places, probably better than few other of you, which may surprise you, because I love the nature in California. So I know quite a lot of places anywhere along the Eastern Sierra Nevada, the 395 from the Mono Lake to Bishop to the Mammoth Lakes to a lot of places that can be seen. But my involvement in AeroE was amazing since I published for the Journal of AeroE. which is the American Institute of Aeronautics and Astronautics. But little did I know how many programs they have for educators and for university students, and how welcoming AeroE is. I have to say, they've been almost like my family, I have to say. So that's warmly recommended for those of you who would like to study and pursue your studies. It doesn't have to be preferably in aerospace and aeronautics, but we have a lot of members from around the world. As I said, 30,000. What I do there, I try to do my best. I do background research, write technical papers and review interesting articles. And Ken, that is the engine of AeroE, I would say, the eternal engine. He assists with all the events and helps all of the people that are involved with whatever needs to be done. So I would say being involved in an organization is important, because it makes you feel like you're in a family. You learn, you exchange ideas, and you don't know, tomorrow one of those members may lead you to your job. So and it's also a personal and career development. So I would highly recommend that. Recent articles that can help me to publish in the newsletter, it's biomimicry examples from engineering. That was quite a few pages, but interesting. And the article I'm working on at the moment is the solar power in the sky. Basically, all the solar power that is used at the moment on aircraft and anything that flies. A few examples would be Airbus Zephyr, that has been flying continuously for 26 days, which is incredible. The solar impulse from Switzerland that actually navigated around the globe in a few stops, and highest altitude, the NASA's Helios, the god of the sun in Greek mythology, that reached an altitude of 96,000 feet, which is incredible, all using solar power. That's what I want to the young generation to know, that we can actually use the sun's power, and we only use few % of the solar energy now, the energy that is available. The rest, unfortunately, is coal power and the power of the ancient marine organisms, included oil, which we should stay away from. Few words from Glendale Community College, that has a great engineering department, included robotics, programming, and 3D printing, which is fascinating. 3D printing and modeling is used nowadays everywhere in the industry, including space. And these are a few. So they have civil engineering, computer engineering, electrical engineering, mechanical engineering, and software engineering, and so on. And they have close connections with JPL and the rest of the companies. So engineers at work. Here are a few pictures. I often get questions, what do you do simulations? Do you simulate reality? Is this real? I would say yes, absolutely, it's real, but we are simulating reality. It is not exactly reality. It contains some errors and some estimations. So we cannot exactly 100% predict whatever is happening in whatever we are designing, but it's pretty good and it's advanced depending on the tools and knowledge. So a few examples are computer simulations are big and are used in every industry, included the space shuttle and the heat shield design. So nowadays, you don't actually manufacture initially because it's too costly. You actually start to initially dream and do Leonardo da Vinci sketches. No, I'm not joking. Most of the engineers, included me, use simple pen and paper and get your thoughts on a paper of what would you like to change in a design and what problems would you like to solve. And maybe a few equations, but mainly sketches and drawing. And you start to do some computer modeling, and you start to simulate whatever. This is computer modeling, including this fishnet, as I call it, around the car, which is known as a computational mesh. So every single point on this and around this car must be solved using the equations I show you. And that's why you now know that we cannot do it without computers. It would take too long time to solve all the equations for millions of points, especially around such a huge thing as a car. But we can do it, and the results are very good, actually. Depending on what type of software and input, it's comparable to what you would measure in an experiment. And it's not only cars, it's wind turbine, even inside our arteries and heart valves, and around our buildings and so on, and inside the jet engine and so on. So modeling is huge nowadays. Testing, which I also did a lot, is also huge. Testing of anything from jet engine to aircraft to Mars rover, to heat testing of buildings, bridges, and so on, is important and is done. However, this part, modeling, I would say you cannot be and do without it as an engineer. It's impossible. So modeling is done everywhere. So if there's one thing I can recommend engineers, you have to learn to do a little bit of CAD modeling and some basic understanding of simulations of heat, vibrations, flow simulations, because it's really used everywhere in the industry because it's so powerful and cost effective. So those are a few testing. Actually, I thought it was an excellent email I received about the request. What's a regular day at work? Well, regular day at work would involve this. It would involve that. If you ask, what is this? It's a spinning propeller. In this case, it is to generate electricity. So I worked in Sweden at a company known as Seatward to design giant floating wind turbine. And if you think, why would you need a floating wind turbine? It's complicated enough to design a wind turbine that is on land that you see here in a desert and everywhere around us. Well, it's simple answer, because out in the ocean, you have no terrain that actually blocks the wind. So the wind velocities are much higher, less turbulence. It means less vibration and less fatigue on anything that is floating. And just to give an example, so a doubling of the wind speed, so from 2 meters per second to 4 meters per second, would give you 8 times the power. So the power you extract has a cubical relationship with the wind velocity. So it means if you have higher wind velocity out in ocean, that's why you can extract more energy basically in an offshore wind turbine. So this is a regular day at work. If you're wondering, what is this strange thing? Is this artwork? Kind of, it's an engineering artwork. What you see here are 3 wind sections of a wind turbine. Think of it as an aircraft wing, and you slice it like you slice a loaf of bread. So these are the cross section seen at the elevated view as a bird view, and they are rotating. And the flow is actually, the wind is coming from left to right in a picture. So you have so this is how engineers nowadays simulate a wind turbine. And what you see here is the pressure and the complex changes in the forces when the 3 blades rotate around the circumference. This is one of the things engineers like me do nowadays to try to predict the forces and the loads and the dimensions and the effects and the safety margin of anything. In this case, it's a floating wind turbine. I had more headaches than the wind, I have to tell you, because as you know, if it's floating out in ocean, It's not just the wind and the wind gust and the turbulence and the lightnings. It's also, since this is Nordic country, it was ice loads, it was wave loads and slamming, it was current, it was tidal current and so on. So it was extremely challenging, but rewarding. So I don't think students should be afraid of taking on challenges. This is a sample of day and my hand calculations for the volumetric flow. I have to be honest, you don't use equations and definitely not calculus every day, but it does happen. Just to check your thoughts and simulations, it does happen, but it's more unusual, I would say. It's more the physical understanding that is important. Simple things like the conservation of energy mass is actually missing from young generation. So my advice to you, study your basic physics, whatever you do, whether you're doing in medicine, chemistry, physics. So just study some basic physics, and it will take you long, included the conservation of mass, energy, and momentum that can be applied to anything in order to get understanding, does this make sense, the result? So I often actually don't look into this, which is the fishnet, a mesh. Again, what you see is 3 blades represented or surrounded by all this mesh or fishnet or computational mesh. This is another picture of a computational domain or mesh that is known in computational fluid dynamics. This can be, by the way, anything. It doesn't have to be just a flowing wind or current. It could be anything that flows or anything that has to do with density, heat. So it doesn't just have to be. And the area in a dark green is the rotating region. And the rest is, so you have flow from left to right, and the sections of the wind turbines are rotating in counterclockwise location, and in center you see the tower. So this is to represent a section of a vertical axis wind turbine. And if you wonder what's the point of this, I often get this question from project leaders and CEO. What is the point of all this? This looks like fishnets. Well, the point is that you can predict the loads and forces before you actually spend millions to design and test it. And for you to know how delicate this is known as a boundary layer. If you see, it's you have many more thousand cells. The closer you come to the actual airfoil or the section of this blade, that's where you have the most friction and viscosity. So you see that it's much finer the closer you come to the structure. That can, so this is also one way I would say engineers talk to each other. This is engineering language. It's basically interpreted the results, doing your own hand calculations, especially using Excel or any other tool, to actually come up with the numbers. This is about wind velocity, the shedding frequency, but it could be anything. This is just a regular day for an engineer, because we don't actually talk by saying that I think, or engineers don't usually say that I don't think this is the way. So sharing opinion, you can do that during the lunch break. We do that too, we're not that boring. And we can even joke about the data. But when engineers have a serious talk, it's talking with the numbers and logic and using science. So opinion does not matter. I think it's not, or I think it is, does not have any value. So saying that something is has a high speed or velocity doesn't have any meaning for engineers. You need to put a number on it, saying that something travels at Mach 25, which is 25 times faster than the speed of sound. Then you start to understand, wow, that would develop shock waves and so on, like the space shuttle upon re-entry. So numbers are important, and you have to do your homework. So before you present, numbers are as good as the input or the engineer that use it. So if you think this is just a magic, it's not. You should use your logic and gut instinct. I would say don't go and ask Uncle Google, and don't start to look into the books. Close your eyes and ask yourself, does this make sense? Is this, if you think about the gut instinct, the engineering judgment, or the scientific judgment, or understanding of anything you know, does this make sense? If it doesn't, you should definitely look into it, because that's what your unconscious is telling you, that you should look into. Some of these numbers does not make sense. You don't have to prove it. That's what I would say as an engineer working many years. It's that has saved me and the companies I work for. It's not actually spending hundreds of hours to do simulation to show the leaders that, look what I've done, these are the loads. I often actually start to think in very basic terms, are these numbers correct? Does it make sense? Can it actually physically be that big or that small? If yes, that's where I go to next step and plot the results. And I compare with the experimental data, compare with the simulated data, especially the experimental data, and see, okay, now we are into something. What you see here are the storm loads. So basically, vertical axis wind turbine has, in this case, 3 blades, and you stop the wind turbines at a certain speed, usually at 25 meters per second. It sounds strange or funny to you guys. If it's windier than 25 meters per second, they stop all the wind turbines. It is really weird for all the engineers that don't work with this, but it's for safety reasons and for structure reasons, because the structure cannot take the loads and the vibrations. So what this actually says, especially for the young students, how can you use this? What's the point of this graph? What this says is actually something remarkable. So if you were going to design wind turbines that I did, they're actually working on it now in Sweden to do some testing and manufacture it next year. It's a 1 megawatt floating wind turbine. And it will be placed, unfortunately, in Norway, not in the country I grew up in, Sweden, due to a lot of complicated laws. But what this says is powerful. That's what I try to tell our CEO, that this simple graph tells this, that what you see here on the x-axis, on the horizontal axis, is that azimuth angle basically is the position of the blades around a circle. So if you see the blades rotate like a clock, so 360 degrees, as you see. And where should you not stop? So if you stop the blades when it's really stormy at 25 meters per second, where is the absolute worst place to have the blades? This is one type of engineering questions that the young generation, especially young, bright engineers, especially from the best institutions, from Stanford, MIT, Cambridge, that I had the opportunity included, Chalmers University, or the least optimum position of the blades, we should not have for structural reasons, because it would be dangerous to actually, and most of them say, can we get some input? I said, well, you have to search the input for yourself. So what this says is something remarkable, is that at 260 degrees, so let me see if I have somewhere. So this is the azimuth angle, by the way, and you see the blades in cross section from a top view on the right-hand side. On the left-hand side, you see the tower in the center. It's a flow simulation, and the 3 blades that are rotating. What this says is that if you stop the wind turbine blades and happen to, not know the fact that I presented for our company at exactly 260 degrees, you will have a failure of structure and lose millions of dollars or whatever currency you're using. And most importantly for me as a responsible engineer is the impact on a society and human life, because well, we designed it, or I designed it as an engineer, and I should do my homework, especially for the safety. I actually, first thing I do, I check for safety. Concerned is not actually profit driven. My way of thinking is think safety first and human life, whatever you're designing, and the long-term use. The second part is the efficiency and so on, and even aesthetics. So this graph is actually remarkable. That's what they use now. So they know they should not stop the wind turbine at that angle, because it will not be able to withstand the storm loads and you will have a collapsing of the structure. That's how powerful simulations and knowledge can be if you know how to use it correctly. These are a few input. As I said, engineers like to talk numbers. And when you present something, all of the engineers, especially experienced engineers, said, what was your inputs? Because it may make a big difference in your assumptions, anything from fluid viscosity to density and so on and so on. So that's important. This is real life solution from engineering. It's the problem. We had a actually major issue with straight blades and something known as wingtip vortices. You see on the right hand side a beautiful image. This is a visualization of a flow around the aircraft wing, and you see this vertical, almost like a tornado flow around the wingtip due to the changes and difference in pressure between the upper side of the lifting wing and the lower. So you have a lower pressure on the top surface of aircraft and higher pressure on the bottom, and at the tip it starts to leak. So the leaking of the pressure and trying to equalize creates actually a tornado-like structure, which you don't see when you take off or land, but it is there. So I thought to myself, we have 3 straight wings because that's the most efficient. It's not most efficient design for a wind turbine blade. However, it's the most efficient and cost-effective and safest way of doing it. Otherwise, you could do a version of helix and so on, which we also tried, but it becomes too expensive to manufacture. However, so this was the task our project leader gave me. This is the real life engineering problem, just to give you an idea what the engineers do. So he told me we have to solve this situation with the drag and the problem, because it slows the wind turbine blades down and we generate less electricity. Can we do something about it, right? I said, well, I'm not a magician, but I would try. So what I did was to try to use my curiosity and imagination, looking into not manuals and engineering books and asking Uncle Google, to look into nature, look into eagle and the rest of the birds. What do they have around their wingtips? Well, it's certainly not strange devices. They have feathers that are flexible, and that's what they use to fly efficiently and have been doing so for billions of years. And that's where we have to learn. So I did this strange serrated design, which our project leader loved. And this is an example of if you've been flying, you may have seen the winglets, the bent wingtips on aircraft. Those are there not just for aesthetics or that it looks cool. They have a huge effect on reducing fuel consumption and air resistance or drag. And on the lower right, you see the difference of a conventional wingtip without the bend or winglets, and on the right-hand side. So it basically reduces something known as induced drag. Basically, think of it as a rubber band. So the air and the air resistance is like a rubber band. It tries to stop the aircraft from moving forward. And this is one way engineers do it. Almost all the new aircraft, they have several versions of these winglets. However, I looked into the nature and tried to solve it instead of doing and using the same winglet design that Airbus and Boeing and the rest of the aircraft company have been doing, which I think is important. These are a few images of the winglet vortices, especially this is a real aircraft visualized by, and this is the low and high pressure I mentioned to you guys. This is, by the way, flow visualization of the wingtip vortices or the tornadoes from the wingtips as we had on our wind turbine blades. A great day at work. What was it? Well, as you know, wind turbines, left-hand side, the one I helped design, floating vertical axis, so the one with 3 straight blades or any other shape, or horizontal axis that are more common, both offshore and onshore. But they have one thing in common, which I didn't like, unfortunately. As I said, I'm not a traditional engineer. It's the tower and the center of gravity. You have huge mass generator on top, a few hundred feet up in air, and this is floating. It's anchored to the seabed, but it's floating and it's moving with waves and currents. That's one issue I had. So huge difference, and center of gravity is too far up for me. And it was also the shape of the tower, and that was my task at this day. And I'm not kidding, it was the saguaro cactus that inspired me. Strange connection, you might think, because most towers, if you look on a flagpole and tower, wherever you are, you would see this straight tapering steel design that they've been using for hundreds of years. So I asked myself, where in nature do you find a design that can withstand the forces of the wind and nature? Well, it's in Arizona and Utah desert. This is saguaro cactus that stands tall despite that you have gusty winds and it's open terrain. And it's this corrugated design that caught my attention and many other researchers. On the image here, what you see is something known as karma vortices. It's basically the way the flow behaves around the cylindrical object. And what you see here is a beautiful example of the symmetric and organized vortices that look beautiful, but may be dangerous for structures. Why? Because it may start to vibrate. So if the frequency of these shed vortices from the cylinder or any cylindrical object, not only circular in cross-section, if that is similar to the natural frequency, so every structure has a natural frequency or a few natural modes of frequencies. So if the frequency of the shed vortices is matching the natural frequency, that's when engineers start to say, OMG, that's dangerous, because it has happened in the past that is known as resonance. So it starts to increase in amplitude and things may start to fail and collapse, as they did at I think it was 1940s in Tacoma Narrows Bridge that collapsed due to exactly this phenomenon known as vortex-induced vibrations. So even wind can be dangerous for any tall structure if you don't know how to tame nature. So I looked into the saguaro cactus. I had a lot of laughs from my CEO and project leader. However, I do always my homework, and I always ask myself, are we the first one to design tall structures? Definitely not. There are a lot of trees and cactuses have been there for millions of years. Why don't they have smooth structures like we do design towers? Well, you tell me, because it's been there for millions of years. And only recently, actually, researchers have started to look into this, included Stanford and a few other places, about the shape of the cactus compared to a smooth shape that intuitively a lot of engineers design and think that has the least resistance and the best design. But it turns out that the shape of cactus actually reduces this oscillations and vibrations and even has less drag. So that explains the cactus magic trick, how it can withstand the winds in Arizona desert. But do we learn from it? Unfortunately not. Engineers still design the steel structures like they do. Some civil engineers have started to look into this for tall buildings. Now to my favorite subject. I'm sorry, it's a little bit over time.
Yeah, Mike, it's getting really late, and I wanted to have a little chance for the students to ask questions. So I'm curious if you can take questions now.
Absolutely. Can we do 5 minutes on biomimicry before we take questions? Is that okay?
Let's check with the students. How are you guys doing? Good? All right. So okay. It looks like they say, go ahead, give it. I think this will be really fascinating for them.
Excellent, because this is one of my fascinating subjects. Okay, this is about biomimicry and nature-inspired design, which I think all of you should look into. It's the study of the processes in nature that has gone through billions of years of evolution. It's not copying the design, it's taking inspiration from it. Everything from the V formation of the birds that actually migrate thousands of miles to the beautiful bird, to the tardigrade, to even gecko and gecko feet that they've used this for space applications and robotics, to the beautiful abalone shell that is the best composite materials in nature. By the way, why this beautiful toucan has such a long beak is not just that it's that strong and light, but it also uses it to dissipate heat. And a few other examples. You have the termites in Africa that use passive cooling without any electricity. You have the dolphin and the sonar that can be used to detect tsunamis. You have the wavy leading edge of the hammerhead shark that have been used, and the pectoral fin of the whale that have been used on wind turbines to increase efficiency. You have the whiskers of the California sea lion that are wavy. So if you look at the cross-section, they are wavy to reduce vortex-induced vibrations. They use that to sense pressure and vibrations in the water. How about the serrated wing of the owl that may be used to silence anything from fans to aircrafts? How about swimming fish that swim in thousands without colliding and so effortlessly that can be used for wind turbines? How about this that is my favorite that I've used for the high-speed train in Japan, is the kingfisher and the design of this high-speed train to reduce shock waves in tunnels. And the boxfish that Mercedes-Benz and Bionic car. How about the dolphin and the air bubbles to reduce friction? How about the smoke beetle that uses its incredible detection to detect smoke fire to lay its eggs? How about the hydrophobic design of the lotus flower and the moth eyes to reduce reflection that has been used on solar cells and cameras for astronomers? And the Namib desert beetle that actually drinks from fog without actually any water, without any electronics or advanced, it literally drinks from fog. How about the pomelo fruit that has been used as impact resistant helmet, and the coconut shell that has been used to reduce crack propagation and may be used in earthquake safe buildings, and the slugs and mollusks and the underwater glue without any heat or chemicals that is actually being researched on for surgical and medical application. That's the pomelo fruit. And that's where I would like to finish, because I promise you guys, I have a lot more, but I want to honor your time, and I want to thank all of you for listening. I think this will be another talk on renewable energy and global warming and the rest of the slides I have. But my appreciation to all of you guys. Thank you all for your attention and listening. I hope it was fascinating to hear from an engineer in a field how it is to work as an engineer and what you need to learn and in order to move forward and progress. Thank you all for listening. It was a pleasure for me.
Yes, thank you so much. This was very, very informative. And as an engineering major myself, very, very, very helpful. Um, it's nice to see. I've heard from people in civil engineering where you need to be fluid a little bit, and there are different domains within civil engineering, but it's only focused on that major. So it's nice to hear that you can cross major, and that's probably what I want to do. I just want to learn everything I can about the major I'm in currently, and then work on branching out and just explore what the skills I have. So it's nice to see you're sort of a role model for me actually right now, which is fascinating because you've done so much. So.
Oh, thank you. I appreciate it. I feel honored to hear that. Yeah, absolutely. If you're into civil engineering, that's actually one of the oldest. So it's been used in many, many places. Anything from the passive buildings in Africa that are learning from the turbines to windows that actually reflect, to shades that actually change using actually nothing else than the pine cone. So next time you see pine cone, I hope you're thinking about me. Pine cone doesn't have anything inside, but it opens when it's dry and low humidity to release its seeds. That's fascinating design. So that's a passive design that may be used in shades, in buildings, and many other things. So really, really, I'm honored that at least I've been inspired few of you to search beyond the books and beyond Google, to progress, to think outside the box, to even go into other fields, especially into nature, because there are a lot of designs and answers that we actually don't see.
So I've got a question in the chat. Do you have any suggestions on what computer program engineers should learn to help with their jobs, right? So how can they diversify?
Absolutely. I would say if you look into computer programming, it's absolutely a lot of the scripts from MATLAB and Python and C+ and Fortran and so on. However, what I would recommend is not only looking into scripts, but see the implication of the predictions. So all the programs that do magic that have been even enabled JPL and NASA scientists to land on Mars, which is spectacular achievement, but to actually look and see the power of it, not only looking into the scripts of it, but looking into the application of it. So how can you use this to maximize and make designs more efficient, not only in terms of software, but in terms of the actual design of it. It may even be into actually one thing I can mention. I had a student at Chalmers University. He was a mechanical engineer, but his dad was a doctor. And he started looking into the propagation of diseases, actually. So he started to do programming, how bacteria spread on the surface and so on. And it was fascinating to see that as a mechanical engineer or software engineer, you can use that knowledge, but you need to do some reading in the subject you are doing in order to be able to talk the same language with whatever subject it is. And go with your passion, I would say. And you will find the knowledge there.
So I think, Gabriela, you had some questions you wanted to get in. Let's take your questions, and then I have one more in the chat too.
Yeah, I'll just ask one question. I think it's very powerful that you use your instincts and your inner subconsciousness to guide you. And my question, well, it's kind of two questions in one. Have you always had this ability and confidence to use that knowledge within you? And the second one was if you have ever suffered from imposter syndrome.
Absolutely. I would say no. I have to be honest. I haven't always had this ability. But initially, actually, for many years ago, when I was a young student, looking into all the equations, and it gives you the power, you think you can predict anything in the world. However, life proves and shows you that we can only actually predict and understand a small part of the universe. Just to give an example, everything we see around us, including stars and galaxy and all the materials, is just 5% of the universe. The rest, we don't actually know even what it is. We call it dark matter and dark energy, but we don't know what it is. So I would say, no, it took time for me, but I start to, instead of relying too much on equation and the power of the book and knowledge, to actually listen within myself and my unconscious, that does this make sense? Without doing actually any calculation, I usually close my eyes and said, does this make sense? Could this actually happen? And what can we do about it? Where in nature would you find this? And I think our unconscious is way more powerful than we can ever imagine if we listen to it. We often don't and rely on books and nowadays on the internet, and we become passive. So I think we have to, instead of doing the equations and simulations, we have to actually listen within ourselves and think, does this make sense? I think that's really, really important. I think I would say that gut instinct and feeling, I can't often actually even say before I do, but it often nowadays it comes to me. I said, no, but that could be dangerous. Just to give you a short example, this floating wind turbine had a rotating underwater section that makes it float. It's like a long cylinder on the water. And I didn't think of it as such, but just closing my eyes made me think about a golf ball that spins. So a golf ball that spins, it has nothing to do with the wind turbine, but somewhere in my unconscious was that, yeah, a golf ball, it can travel far, not just because you have the best golfer, because it spins, it generates extra lift. And it's the same thing for the wind turbine. And that may be kind of, it may be something that not many engineers would think about in the first place, because the wind turbine was to generate electricity. But in my mind, it was the connection with the golf ball and my unconscious, but this can be dangerous. You have a huge structure that is rotating with all these forces. I better look into some details. So I would say let your unconscious guide you in the first place, because it's often right, I would say. Your knowledge and experience can be misleading. However, your unconscious, if you listen to it, it's almost never wrong. So the gut instinct you have about a person, a project, or a job is often the correct one, if we listen to it.
Thank you.
And she had a second question. Have you ever felt the imposter syndrome?
Absolutely, absolutely. I have. It happens often that you that you encounter real life situations that makes you think, what should I do now? So absolutely, I have absolutely felt that.
And we have, we've got in the chat, we have a question again about diversification. So should engineering majors, right? So you get a bachelor's degree and then you go to get your master's degree. And so as you go through in your master's degree, should you alter your major to diversify? For example, many famous aeronautical engineers got their bachelor's degree in mechanical engineering, but then afterwards mastered in aeronautical engineering.
I would say yes, absolutely. That helps a lot, without a doubt. But to tell you honestly, you can do that on your own. So you don't need a degree. Just to give an example, I was working for Volvo trucks to basically reduce something known as soiling. Basically all the splashing that occurs when a truck or car goes through mud, dirt, water, rain, etc. It's all that splashing. They want to reduce it because it increases visibility for safety. And for me as an aeronautical engineer, I could simply look into the design, the aerodynamics, make it the most fuel efficient. However, I noticed that I need some knowledge in chemistry. Why? Because it had to do with surface chemistry of the windshield. So that's why I did what I did. I started to read about surface chemistry, how water actually slides on surfaces, how it's affected by anything from dust, pollen to dirt, and so on. And you can learn quite a lot actually by, if you have the passion and interest, you don't need the actually specialized degree. What you need is a main degree. And once you start working, you can diversify and learn new things. In fact, you're forced to do that. So if you would ask a JPL engineer if they work on robotics, if that's all they do, they would probably laugh and say, definitely not, because you need to look into anything from even biology, from the ionized radiation from space, so the effect it has on humans. I would definitely look into tardigrade and other animals that shield themselves. And you would definitely look into the material, even the psychology, the ergonomy of whatever you are designing, the electronics of it, the chemistry, the environmental impact, the recycling, even the cost and so on. You need to do a cost analysis. So you cannot just do programming and do tell a robot arm to move something. That's unfortunately, or fortunately, if you ask me, that's not engineering, advanced engineering works nowadays. You are forced to actually learn, which is fantastic. So you exchange ideas with colleagues in many other divisions, and that makes it a much, much better design. So no, I don't think you need to diversify, have 5 master's degrees. You need a main degree. It doesn't definitely have to be a PhD. It doesn't even have to be a master's. It would be excellent if it is, but it doesn't have to be. However, being curious and learning during your job is the most effective way of doing it, because that means you can communicate with your colleagues, be in the project, and that's extremely valuable because they know that you can be in many different shoes in a company or a project. That's very valuable. So no, I would say don't spend many years on a 5 PhDs. You would have a gray hair. So no, one basic degree is enough, but try to be curious and diversify and learn from other subjects every day. And you will become better and better at many, many, many things at the same time. Okay, any more questions?
I think there's nothing left in the chat. Anyone else? Go ahead and unmute, or you can put it in the chat if you don't have a speaker. Excellent. Well, I would just like to thank you so much for coming, Vahik. This has been like just so fascinating. And just wanted to add one thing is that when you were talking at the end about just your experiences that you have, it's true. I mean, I have a master's degree in math, but I also have a lot of other experiences, right? I used to be a kayak guide. I was in the Peace Corps, and like all those experiences add to your collective knowledge, and that moment when you close your eyes and say, is this the right way to go, or do I need to watch out for something dangerous here, right? So those experiences, I think they really add to that. All right, everybody, let's give Mike a big hand and tell him thank you.
Thank you so much, Vahik.
Guys, appreciate it. It was an honor and pleasure. Thanks all for your time and listening. Probably there will be another presentation on climate change and renewable energy, because that is also a hot topic, and especially the young generation think this is just a theory or just a hoax or joke, but unfortunately the bad news is that it is happening at the moment, and it will happen for our kids and grandkids and so on if we don't act and react. So I think without being an environmental extremist, I would say if you're going to change or do any subjects, you will, without a doubt, be involved in some form of environmental science, because that's part of future, both in terms of energy generation and our adaptation to society to more renewable and environmental friendly ways. So that's what will be next time. I had them in the slides, but
yeah. No, we'll connect you for sure. That would be fantastic. We also have a sustainable club at Cabrillo, and it's actually headed by one of our engineers in the engineering department. The faculty is the moderator for that club, and so without a doubt, I'm sure that they'll try to reach out. Right now we're under a grant to allow us to have these colloquiums, and so we hope it continues next year, and we'll definitely keep you on the roster.
Absolutely, absolutely. Appreciate it. Thank you guys all for your time, and have a good evening until I see you next time.